Welcome friends. Today we will discuss mutual independence of events and Bayes' theorem. We already discussed the independence of two events A and B. By definition, two events A and B are said to be independent if P of A intersection B equal to P of A into P of B, where P of A not equal to 0 and P of B not equal to 0. In this module, we extend the concept to more than two events. Mutual independence. Mutual independence of three events A, B and C. Three events A, B and C are said to be mutually independent if P of A intersection B equal to P of A into P of B, P of B intersection C equal to P of B into P of C, P of A intersection C equal to P of A into P of C, and P of A intersection B intersection C equal to P of A into P of B into P of C. Condition 1 is the condition for pairwise independence of A, B and C. Mutual independence of n events. The events A1, A2, etc. An in a sample space S are said to be mutually independent if number 1 P of AI intersection Aj equal to P of ai into P of aj for I comma j equal to 1, 2, etc. n, where I not equal to j. There are NC2 such conditions for various values of I and j. Number 2, P of ai intersection aj intersection ak equal to P of ai into P of aj into P of ak for I, j, k equal to 1, 2, etc. n, where I not equal to j not equal to k. Such NC3 conditions are there for various values of I, j and k. Finally, P of A1 intersection A2 intersection etc. intersection An equal to P of A1 into P of A2 etc. into P of An. We observe that for the mutual independence of n events, a total of NC2 plus NC3 plus etc. plus NCn, that is equal to 2 raised to n minus 1 minus n conditions are to be satisfied. Pairwise independent need not imply mutual independence. See the following illustration for three events A, B and C. Illustration. Consider the random experiment of tossing of two unbiased coins. The sample space of the experiment is the set S contains ordered pairs HH, HT, TH and TT. Since the coins are unbiased, the four possibilities are equally likely with probability 1/4 each. Consider the events A contains the ordered pairs HH, HT and B containing the ordered pairs HT, TH and C containing the ordered pairs TH and HH. Then probability of A equal to probability of the set containing ordered pairs HH, HT, that is equal to probability of the ordered pairs HH plus probability of the ordered pairs HT, that is equal to 1/4 plus 1/4, that is equal to 1/2. In similar way, probability of B equal to probability of C, that is equal to 1/2. A intersection B equal to the set containing the ordered pair HT. This implies probability of A intersection B equal to 1/4. That is equal to probability of A into probability of B. B intersection C equal to the set containing the ordered pair TH. Therefore, probability of B intersection C equal to 1/4. That is equal to probability of B into probability of C. A intersection C equal to the event containing the ordered pair HH. This implies probability of A intersection C equal to 1/4. That is equal to P of A into P of C. A intersection B intersection C equal to null set. This implies probability of A intersection B intersection C, that is equal to 0. But P of A into P of B into P of C equal to 1/2 into 1/2 into 1/2, that is equal to 1/8. This implies probability of A intersection B intersection C not equal to P of A into P of B into P of C. Now we can conclude that A, B and C are pairwise independent but not mutually independent. That is, pairwise independence of events need not imply their mutual independence. In order to enhance the concept of mutual independence, we shall look out the following problems. If A, B and C are pairwise independent and A is independent of B union C, prove that A, B and C are mutually independent. Proof. Given A, B and C are pairwise independent, this implies P of A intersection B equal to P of A into P of B, P of B intersection C equal to P of B into P of C, P of A intersection C equal to P of A into P of C. To prove A, B and C are mutually independent, it is to show that P of A intersection B intersection C equal to P of A into P of B into P of C. Consider A and B union C. P of A intersection B union C equal to P of A intersection B union A intersection C. This implies P of A intersection B union C equal to P of A intersection B plus P of A intersection C minus P of A intersection B intersection C. Using number 1 in number 2, we get P of A intersection B union C equal to P of A into P of B plus P of A into P of C minus P of A intersection B intersection C. Let it be equation number 3. Given A and B union C are independent, hence P of A intersection B union C equal to P of A into P of B union C. P of A intersection B union C equal to P of A into P of B plus P of C minus P of B intersection C. Since B and C are independent, P of B intersection C equal to P of B into P of C. This implies P of A intersection B union C equal to P of A into P of B plus P of A into P of C minus P of A into P of B into P of C. Let it be equation number 4. Comparing equation number 3 and equation number 4, we get P of A intersection B intersection C equal to P of A into P of B into P of C. Hence, A, B and C are mutually independent. If A1, A2, etc. An are n independent events with respective probabilities P1, P2, etc. Pn, show that P of A1 union A2 union etc. union An equal to 1 minus P1 into 1 minus P2 etc. into 1 minus Pn. Proof. By De Morgan's law, P of A1 union A2 union etc. union An, the whole complement equal to P of A1 complement intersection A2 complement intersection etc. intersection An complement. This implies P of A1 union A2 union etc. union An equal to 1 minus P of A1 complement intersection A2 complement intersection etc. intersection An complement. Let it be equation number 1. Given A1, A2 etc. An are n independent events and then A1 complement, A2 complement etc. An complement are also independent. Hence, P of A1 complement intersection A2 complement intersection etc. intersection An complement equal to P of A1 complement into P of A2 complement into etc. into P of An complement. This is equal to 1 minus P of A1 into 1 minus P of A2 etc. into 1 minus P of An. That is equal to 1 minus P1 into 1 minus P2 etc. into 1 minus Pn. Now, equation number 1 implies P of A1 union A2 union etc. union An equal to 1 minus of 1 minus P1 into 1 minus P2 etc. into 1 minus Pn. A problem is given to 3 students A, B and C. They are trying to solve the problem independently. Their respective chances of solving the problem are 1 by 4, 1 by 2 and 3 by 4. Find the probability that the problem is solved. The solution. Let A, B and C denote the event of the problem is solved by the student A, B and C respectively. It is given P of A equal to 1 by 4, P of B equal to 1 by 2 and P of C equal to 3 by 4. The event of the problem is solved occur when the problem is solved by any of A, B and C. That is, the occurrence of the event the problem is solved is equivalent to the occurrence of A or B or C, which is the occurrence of A union B union C. Hence, P of the problem is solved equal to probability of A union B union C. Since A, B and C are independent, P of A union B union C equal to 1 minus P of A into 1 minus P of B into 1 minus P of C. This implies the required probability is 1 minus of 1 minus 1 by 4 into 1 minus 1 by 2 into 1 minus 3 by 4, that is equal to 1 minus 3 by 4 into 1 by 2 into 1 by 4, that is equal to 1 minus 3 by 32, that is equal to 29 divided by 32. Bayes' theorem, introduction. Bayes' theorem was introduced by the British mathematician Thomas Bayes. Consider the sample space S of a random experiment. Let B1, B2, etc. Bk are the k mutually exclusive or disjoint partition of the sample space. The figure shows one of such partition. Now consider an event A of this sample space. Let it be as in the figure. Here, the event A can happen only through any of the shaded portion. Hence, A can be expressed as the union of the disjoint areas shaded in different colors. They are A intersection B2, A intersection B3, etc. A intersection Bk minus 1. Hence, A equal to A intersection B2 union A intersection B3 union, etc. union A intersection Bk minus 1. Or A can be expressed as A equal to A intersection B1 union A intersection B2 union, etc. union A intersection Bk, where A intersection B1 equal to null set and A intersection Bk equal to null set. In a similar way, any event A of this sample space can be expressed as A equal to A intersection B1 union A intersection B2 union, etc. union A intersection Bk. Since A intersection Bi's are mutually exclusive, P of A equal to P of A intersection B1 plus P of A intersection B2 plus etc. plus P of A intersection Bk. Here, the probability of the event A is expressed as the sum of compound probabilities. Compound probabilities are the probability of the simultaneous occurrence of two or more events. If A and B are two events, then the probability of the occurrence of A and B together, P of A intersection B, is a compound probability. Bayes' theorem. If an event capital A can happen if and only if one or the other of a set of mutually exclusive events B1, B2, etc. Bk happens, where P of Bi not equal to 0 for I equal to 1, 2, etc. n, then P of Bi given A equal to P of Bi into P of A given Bi divided by sigma I from 1 to k P of Bi into P of A given Bi for I equal to 1, 2, etc. k. Proof. By multiplication theorem, we can express the compound probability P of A intersection Bi as P of A intersection Bi equal to P of A into P of Bi given A, that is equal to P of Bi into P of A given Bi. Let it be number 1. This implies P of Bi given A equal to P of Bi into P of A given Bi divided by P of A. Let it be number 2. Since A can happen if and only if one or the other of a set of mutually exclusive events B1, B2, etc. Bk happens, where B1, B2, etc. Bk are mutually exclusive, A can happen only through any of the k mutually exclusive ways A intersection B1, A intersection B2, etc. A intersection Bk. Therefore, P of A equal to P of A intersection B1 plus P of A intersection B2 plus etc. plus P of A intersection Bk. That is, P of A equal to sigma I from 1 to k P of A intersection Bi. Using equation number 1, we get P of A equal to sigma I from 1 to k P of Bi into P of A given Bi. Hence, equation number 2 implies probability of Bi given A equal to P of Bi into P of A given Bi divided by sigma I from 1 to k P of Bi into P of A given Bi for I equal to 1, 2, etc. k. Hence, the proof. The theorem may also be stated as if B1, B2, etc. Bk are mutually exclusive events such that P of Bi not equal to 0 for I equal to 1, 2, etc. n, and A be any event which is a subset of union I from 1 to n Bi such that P of A greater than 0, then probability of Bi given A equal to P of Bi into P of A given Bi divided by summation I from 1 to k P of Bi into P of A given Bi for I equal to 1, 2, etc. k. Note: one can consider Bayes' theorem when the following conditions exist. The sample space is partitioned into a set of mutually exclusive events B1, B2, etc. Bk. Within the sample space, there exists an event A for which P of A greater than 0. The goal is to compute a conditional probability of the form P of Bi given A. Know at least one of the two sets of probabilities described below: P of Bi intersection A for each Bi, P of Bi and P of A given Bi for each Bi. In the Bayes' theorem setup, if we have an information that the event A has occurred, the probability of the occurrence of A through any of the events B1, B2, etc. Bk, P of Bi given A for I equal to 1, 2, etc. k can be found by the theorem. These probabilities are calculated after observing the outcome of the experiment. Such probabilities are often called a posteriori probabilities. The probabilities P of B1, P of B2, etc. P of Bk are not related to the outcome of the experiment. These probabilities can be found prior to the experiment. Such probabilities are known as a priori probabilities. The terms P of A given B1, P of A given B2, etc. P of A given Bk are the chance of the occurrence of A along with B1, B2, etc. Bk. Such probabilities are called likelihoods. Application problems. Problem number 1. Two boxes contains respectively 2 red, 3 black and 3 blue balls and 4 red, 4 black and 2 blue balls. One of the boxes is selected randomly and 2 balls are drawn. They happen to be 1 red and 1 blue. What is the probability that they come from the second box? Solution. Let B1 and B2 denotes the first and second boxes respectively. Let A be the event of getting 1 red and 1 blue. The event A can happen only through the events B1 and B2. One of the box is selected at random. Hence, P of B1 equal to 1 by 2 and P of B2 equal to 1 by 2. If the selected box was B1, then the probability of the happening of the event A is denoted by P of A given B1, that is equal to 2C1 into 3C1 divided by 8C2, that is equal to 6 divided by 28. If the selected box was B2, then the probability of the happening of the event A is P of A given B2 equal to 4C1 into 2C1 divided by 8C2, that is equal to 8 divided by 28. It is given that the event A has happened. Hence, by Bayes' theorem, the probability of the selected box was the second box B2 is P of B2 given A, that is equal to P of B2 into P of A given B2 divided by sigma I from 1 to 2 P of Bi into P of A given Bi, that is P of B2 given A equal to P of B2 into P of A given B2 divided by P of B1 into P of A given B1 plus P of B2 into P of A given B2. This gives P of B2 given A equal to 1 by 2 into 8 by 28 divided by 1 by 2 into 6 by 28 plus 1 by 2 into 8 by 28, that is equal to 4 divided by 7. Problem number 2. In a lab test on blood sample, it is found that 95% of people with a particular disease produce positive result, but 2% of people without disease will also produce a false positive result. Suppose that 1% of the population actually has the disease. What is the probability that a person chosen at random from the population will have the disease, given that his blood yields a positive result? Solution. Let B1 and B2 denotes the event of a person chosen at random from the population is having the disease and not having the disease respectively. Let A denote the event of getting positive result for one person selected at random. Since the person is randomly selected from the given population, he may or may not have the disease, but it is given that the lab result is positive for that person. Now, to find the probability that he is having the disease, mathematically it is to find P of B1 given A. By Bayes' theorem, P of B1 given A equal to P of B1 into P of A given B1 divided by P of B1 into P of A given B1 plus P of B2 into P of A given B2. It is given that 1% of the population actually has the disease. Hence, P of B1 equal to 0.01 and P of B2 equal to 0.99. The lab gives a true positive result for 95% cases. That is, when the lab tests a person actually having the disease, the probability for getting a positive result is 0.95. That is, P of A given B1 equal to 0.95. The lab gives a false positive result for 2% cases. That is, when the lab tests a person actually not having the disease, the probability for getting a false positive result is 0.02. That is, P of A given B2 equal to 0.02. Hence, the required probability is P of B1 given A equal to 0.01 into 0.95 divided by 0.01 into 0.95 plus 0.99 into 0.02, that is equal to 0.0095 divided by 0.0283, that is equal to 0.3357. Problem 3. The contents of urns 1, 2 and 3 are as follows: 1 white, 2 black and 3 red balls, 2 white, 1 black and 1 red balls, 4 white, 5 black and 3 red balls. One urn is chosen at random and 2 balls are drawn from it. They happen to be white and red. What is the respective probabilities that they are coming from the urn 1, 2 and 3? Solution. Let B1, B2 and B3 denotes the urn 1, 2 and 3 respectively. One urn is selected at random. The probabilities of the selection of the urn 1, 2 and 3 are respectively denoted by P of B1, P of B2 and P of B3. They are P of B1 equal to 1 by 3, P of B2 equal to 1 by 3 and P of B3 equal to 1 by 3. Let A denote the event of getting a white and a red ball. To find P of B1 given A, P of B2 given A and P of B3 given A. By Bayes' theorem, P of B1 given A equal to P of B1 into P of A given B1 divided by P of B1 into P of A given B1 plus P of B2 into P of A given B2 plus P of B3 into P of A given B3. P of A given B1 equal to P of A intersection B1 divided by P of B1. That is equal to probability of a white and a red ball from on 1 divided by probability of B1. That is equal to 1C1 into 3C1 divided by 6C2. That is equal to 1 into 3 divided by 15. That is equal to 1 by 5. P of A given B2 equal to P of A intersection B2 divided by P of B2. That is equal to probability of a white and a red ball from on 2 divided by P of B2. That is equal to 2C1 into 1C1 divided by 4C2. That is equal to 2 into 1 divided by 6, that is equal to 1 by 3. P of A given B3 equal to P of A intersection B3 divided by P of B3. That is probability of a white and a red ball from on 3 divided by P of B3. That is equal to 4C1 into 3C1 divided by 12C2. That is 4 into 3 divided by 66. That is 2 divided by 11. Hence, P of B1 given A, which is P of B1 into P of A given B1 divided by P of B1 into P of A given B1 plus P of B2 into P of A given B2 plus P of B3 into P of A given B3 equal to 1 by 3 into 1 by 5 divided by 1 by 3 into 1 by 5 plus 1 by 3 into 1 by 3 plus 1 by 3 into 2 by 11. That is 1 by 15 divided by 118 divided by 165. That is equal to 33 divided by 118. Similarly, P of B2 given A equal to P of B2 into P of A given B2 divided by P of B1 into P of A given B1 plus P of B2 into P of A given B2 plus P of B3 into P of A given B3, which is 1 by 3 into 1 by 3 divided by 1 by 3 into 1 by 5 plus 1 by 3 into 1 by 3 plus 1 by 3 into 2 by 11, that is 55 divided by 118. And P of B3 given A equal to P of B3 into P of A given B3 divided by P of B1 into P of A given B1 plus P of B2 into P of A given B2 plus P of B3 into P of A given B3, which is 1 by 3 into 2 by 11 divided by 1 by 3 into 1 by 5 plus 1 by 3 into 1 by 3 plus 1 by 3 into 2 by 11, that is 30 divided by 118. In this session, we have discussed mutual independence of events and Bayes' theorem. Before going to the next session, please try to answer the following questions. If A, B and C are mutually independent events, show that A, B complement and C complement are also mutually independent. Two fair dice are thrown independently. Three events A, B and C are defined as A. First dice show an odd number, B. Second dice show an odd number, and C. The sum of the points on two dice. Examine whether A, B and C are mutually independent. Books for your reference are Introduction to Probability Models by Sheldon M. Ross, Academic Press. Introduction to Mathematical Statistics, S.C. Gupta and V.K. Kapoor, Sultan Chand and Sons Publishers. Hope you enjoyed this session. See you next time. Until then, goodbye. Take care.